So we looked at last time how to resolve two forces into a single force using the parallelogram rule. This week we're going to look at how to resolve three forces using the parallelogram rule. So you see we have a given diagram here. There's a 300 Newton force acting in the y direction, a 450 Newton force acting at 45 degrees in the second quadrant, and a 600 Newton force acting on a 3, 4, 5 triangle in the first quadrant. I've started the working diagram, but I have not yet completed it. So down here we've got our working diagram. The first thing that I typically do with the working diagram is provide a sign convention. Now we need to label our forces, and I did so as follows. This is F1 and equals 300 newtons. This over here I called F2 and it equals 450 newtons. And this I called F3, which is 600 newtons. I'm going to call this angle alpha equals 45 degrees. F3 is acting on a 3, 4, 5 triangle. And the last thing I want to do is label this point down here. That's point P, where all three forces are originating. Now, in order to deal with this particular problem, you have three vectors, and you cannot just take all three of them and put them together at once. You have to break them into their pieces. So we're going to deal with F1 and F2 first. In order to use the parallelogram rule with these two forces, I'm going to basically project F1. I'm going to slide F1 over to the tip of F2. I'm going to draw it over there. Likewise, I'm going to slide F2 up to the tip of F1, and I'm going to draw a perpendicular or parallel projection. Where those two lines meet is my new resultant vector, which I'm going to extend up here. I'm going to call that new resultant vector F1, 2. I'm not going to call it FR because that's not the resultant of the problem. I sort of save FR to be the variable that I label the actual final answer with. Now, in addition to labeling those forces, I also need to add some other variables here. So this angle here between F1 and F2, that's beta, and that's also 45 degrees. Now we also need to know some other angles. This angle over here is what I'll call delta. I'm sorry, gamma. And you might wonder how we're going to figure out what gamma equals. Well, that's where a little thing called an auxiliary comp comes into play. Below the diagram, or to the right of it, is also a good place. We're going to have something called an aux comp. An aux comp is where you write things that you wouldn't be able to normally do in your head. They are calculations, but they cannot be the answer. So typically what would go in an aux comp is a calculation of weight based on mass, or a calculation of angles or lengths or something like that. You may not put answers in the aux comp. Now, what goes in the aux comp? I don't grade format in the aux comp. So anything you write in there, this is sort of like a format-free zone. It should be inside a dotted line or a dotted box. And I won't grade the format in there, but your answer needs to be correct. Now, if we look at what we made up here, we made, using F1, F2 and their projections, we made a parallelogram. You recall from trig and geometry that the two opposite sides of a parallelogram are equal, and that the total sum of all the sides inside of a parallelogram is 360 degrees. So using that particular methodology, I can say that gamma equals 360 degrees minus 2 times beta, because that would take care of the other two angles, and there's going to be 2 of that angle gamma, so we got to divide it by 2. So when we do our math there, we're going to figure out that gamma equals 135 degrees. Now there's one more angle I'm going to define, and that's the angle between F12 and the y-axis. Now you might say to me, I thought we had to give our answers with respect to the x-axis. Well, you do, but this is not going to be your answer, and I called that angle delta. So now we need to figure out what F12 is. Okay, and so that's what I'm going to do here. I'm going to have another Roman numeral 2, solving for the magnitude of F12 using law of cosines. So now I've got a triangle, a parallelogram rather, made up of two triangles that I can easily solve using the law of cosines. So F1 comma 2 equals the square root of F1 squared plus F2 squared minus 2 times F1 times F2 times the cosine of the angle that's opposite of F12. So if we look back up at our triangle, let's just for sake of example use F2, the projection of F1, and F12 as our triangle. So I'm outlining it up here. That's our triangle. Now when we look at that triangle, we have two sides, F1's projection, F2, and then the longest side, F1 comma 2. Now that's the one we're solving for. And when we're solving for a particular side using the law of cosines, we want the angle opposite from that side. So the angle that is opposite is this angle gamma here. Whenever you do this law of cosines, you want to make sure that the angle you're using is not touching the vector you're trying to solve. It's across from it, directly opposite to it. So now I've got my equation with my variables solved for my unknown on the left. Now we rewrite the equation, but this time we put in the actual number values. So F1 was 300 newtons. Make sure that your squared's on the outside of the parentheses, because 300 newtons squared is a whole lot different than 300 square newtons. F2 is 450 newtons. Minus 2 times F1 is 300 newtons times 450 newtons times the cosine of 135 degrees. And when you're finally finished, you should find that F1 comma 2 is 695.283 newtons. You also want to make sure to underline any answers 3 times. All your intermediate answers need underlined 3 times. Now you might say, well, why didn't you underline gamma? Once again, that's because gamma was in an aux comp and it is a format-free zone. Now that we've found the value of F1 comma 2, the next step is to figure out what the direction is, the angle. So that's my step 3. And I'm solving for direction delta, and I'm going to use the law of sines. And as you'll remember, the law of sine says the sine of an angle divided by its side inside a triangle equals the sine of another angle divided by its side. So we can say the sine of delta divided by, once again, we need to look at the opposite side. So up here is delta. It's this angle down here. The side opposite it, that it doesn't touch, is this side here, which is the projection of F2. And we're going to set that equal to the sine of gamma divided by gamma. We've already established the opposite side is F1 comma 2. Now if we look at this equation, we know F2, we know gamma, we know F1, 2, but we do not know delta. So we're going to solve this equation for delta. Multiply both sides by F2, and then we have sine of delta equals F2 times sine gamma over F1, 2. Then we take the inverse sine, and we end up with this equation. Delta equals the inverse sine of F2 times sine gamma over F1, 2. Now we've got our equations fully developed with our unknown on the left. We can plug our numbers in. So delta equals the inverse sine. F2 was 450 newtons times the sine of 135 degrees divided by F1, 2, which was 695.283. And when we do that equation, we find that delta equals 27.2357 degrees. Once again, we underline it 3 times. Okay, now we've figured out what F1 comma 2 is. Now we need to go back to our diagram and draw another diagram. This diagram is going to include 2 more forces that we're now going to combine. We're going to include F3, which was 600 newtons, and we're also going to include F1, 2, which is 695.283. Okay, we are not going to redraw F1 or F2. That's a common mistake. A lot of times I'll see students take F1 and combine it with F3. You're counting for F1 twice then. So we're just going to have F1 comma 2 and F3 on this particular diagram. Now, just like before, we're going to want to take F3 and slide it up and draw a parallel line to F1 comma 2. And we're going to take F1 comma 2 and draw it, slide it up to the end of F3 and draw a parallel line there. And where those 2 lines intersect is our new force. And this time I'm actually going to call that force FR, because that force is the resultant force of this particular system. Now we need some angles on here. So let's go ahead and draw the angles that we need. We have the angle over here between FR and the y-axis. That angle I call delta, and that equals 27.2357. We're going to need this angle here, which I'll call epsilon. We are going to need this little sliver between FR and F3, which I'll call lambda. We are going to need this angle here. I called that one mu. And we're going to need this one up here. And I called that one eta. Last but not least, we're going to need the actual answer angle, which is between FR and the x-axis. And that angle I'm going to call phi. There's one more piece of information we need to record in this diagram, and that's my original information about the angle. This F3 was on a 3, 4, 5 triangle. So at this point in time, we go back to our aux comp, and we figure out some of those angles. The cosine of epsilon would equal 3 over 5. So that means that epsilon is going to equal 53.1301 degrees. We can also figure out what eta is. Eta is the angle between F12 and F3. It's the same on both sides because we have a parallelogram. The angle between F1, 2 and the y-axis is 27 degrees. The y and the x-axis are 90 degrees apart, and epsilon is 53 degrees. So we can say that eta equals 90 degrees plus delta. 90 degrees plus delta would give me the angle from F12 to the x-axis. And if we subtract off epsilon, that'll give me the angle between those two vectors. And we're going to find that eta equals 64.1056 degrees. And last but not least, we need to find mu. And we're going to use the same rule that I used earlier. There's 360 degrees in a parallelogram. There are two eta sides, or angles, I'm sorry, and there's going to be two mu angles. So that means that mu equals 115.894. Everything inside the aux comp needs to go inside of a dotted line. Make sure that you use a straight edge for that. So now we can actually go ahead with step 5 and we can solve for the magnitude of FR. Using the law of cosines. So now FR equals the square root of F1, 2 squared plus F3 squared minus 2 times F1, 2 times F3 times the cosine of the angle opposite to FR. If we go up to our diagram, here's FR. The angle that does not touch FR is opposite, and that is angle mu. So now that's our equation fully developed. FR equals the square root of F1, 2 is 695.283 newtons squared plus 600 newtons squared minus 2 times 695.283 newtons times 600 newtons times 100, the cosine of 115.894 degrees. Now you may wonder why I'm carrying 6 significant figures. Remember, I told you the requirement for this class is that you do 4. The reason I keep everything to 6 is because then I know when I round it, it's going to be accurate to 4. You are still only required to do 4. However, I do recommend that you do 6 in the intermediate steps. So when you plug that into your calculator, you should get 1098.99 newtons. Underline the intermediate answer. I do recommend, by the way, that as I'm doing these, you go ahead and calculate the results for yourself to make sure that you can get the same answer that I do. The last step in this process is step 6. And in step 6, we're going to be solving for the direction phi. And we're going to use the law of sines. And as before, we're going to pick 2 angles and 2 sides that we know. Now, in order to solve this problem, we're going to look phi. I don't have any triangles set up by which I can use to solve phi. However, phi is simply the addition of lambda and epsilon. I know epsilon. I can find lambda because it's inside this triangle. In this triangle, I already know 1 angle and 3 sides. So for that particular calculation, we can say that the sine of lambda, and looking at lambda, what's the opposite side? We'll draw a line straight out of that angle, and you will see the opposite side is the projection of f(1,2). That equals, what side angle pair do we know? We know FR and its opposite angle, which is mu. That equals the sine of mu over FR. So then lambda equals the inverse sine of f(1, 2) times the sine of mu over FR. Now we can plug our variables in. Lambda equals the inverse sine of f(1, 2) was 695.283 newtons times the sine of 115.894 degrees divided by FR, which is 1098.99 newtons. Plug that in and you're going to find that lambda equals 34.6903 degrees. As you'll notice, lambda does not actually tell us our answer. As I mentioned, we want to know phi, and phi is the summation of lambda and epsilon. So we're going to solve for phi next. So phi equals lambda plus epsilon. Phi then equals lambda was 34.6903 degrees, and epsilon was 53.1301 degrees. And you're going to find that phi equals 87.8204 degrees. All this information then goes in an answer box. I typically write my answer box at the bottom right of the page, but you can really write it wherever you want on that page. The answer is FR equals 1099 newtons up into the first quadrant at phi equals 87.82 degrees at point P. Remember, we labeled P at the beginning of the problem. The word answer gets underlined, and the whole answer goes inside of a box. Now, a couple of notes just finishing up this particular problem. You notice that phi is 87 degrees, almost 88 degrees, very close to 90 degrees. And the initial problem, you don't actually see this in these notes because I'm trying to make it as straightforward as possible. But in the initial problem, when I drew this diagram, working diagram B, and I extended my vectors, FR actually ended up in the second quadrant. However, when I did my math, I saw that phi was 87 degrees. So that told me that FR is actually in the first quadrant because phi is slightly less than 90. If that happens in one of your problems, you don't have to worry about redrawing your diagram. However, you do have to correctly incorporate the sign into your answer. Once again, the basic principle for this course is your diagrams, they need to be neat, but they don't have to be geometrically accurate. They just have to be mathematically accurate.